The weld was wrong. Southampton Shipyard, November 3rd, 1942. Thomas Robbins was working on his first real assignment. Liberty ship SS Daniel Morgan. Hull section 7B. A practice repair on a section damaged during a German air raid 3 weeks earlier. The damaged area wasn't critical. The ship would be scrapped anyway. But practice was practice. Learn on the disposable ships before working on the operational ones. Robbins was 22 years old. 6 weeks of welding training. Certified 2 days ago. This was his first unsupervised work. The assignment was simple. Repair the damaged hull section. Make it watertight. Demonstrate competent welding technique. Standard procedure for new welders. The damage was typical. Shrapnel from a 250-kilogram bomb that had detonated 40 meters from a ship. The explosion had punctured the hull in 7 places. Holes ranging from 8 centimeters to 35 centimeters diameter. Not catastrophic damage, but enough to sink a ship if not repaired properly. Standard repair procedure. Cut steel plates to fit each hole. Weld the plates over the damaged areas. Test for leaks. Simple metalwork. Basic welding. Robbins had practiced this exact procedure 47 times in training. Should have been routine. But the damaged section was awkward. Located near the bottom of the hull. Difficult access. Poor visibility. Robbins couldn't position himself properly to weld the patches. The angle was wrong. His electrode kept missing the seam. The welds were inconsistent. Amateur work. After 2 hours, he completed 3 patches. All questionable quality. Probably not watertight. He needed a better approach. Something that would work despite the difficult access. He looked around the work area. Steel drums everywhere. 200-liter capacity. Used for fuel storage, water storage, chemical transport. Standard shipyard equipment. Dozens of empty drums waiting to be recycled or repurposed. Robbins had an idea. Not from training. Just improvisation. What if he welded the steel drums inside the hull? Create internal patches instead of external ones. The drums were cylindrical. Easy to position. Easy to weld at their top rim where they'd contact the hull. The drums themselves would block the holes. Provide structure. Make the section airtight from inside instead of patching from outside. It was unconventional. Not taught in welding school. Probably not approved by shipyard procedures. But would work. And it would be easier than trying to position external patches in that awkward location. He positioned the first drum. Maneuvered it through the access hatch. Aligned it with the largest hole. The 35-centimeter puncture. The drum was 60 centimeters in diameter. Large enough to cover the hole completely. He welded the drum's top rim to the hull's internal surface. Circular weld around the entire circumference. The weld was clean. Good penetration. Solid joint. He tested it. The drum was now permanently attached to the hull, covering the hole. Sealed. No water could penetrate where the drum blocked the damage. The damaged section had become an airtight compartment. Not repaired in the traditional sense, but functional. Watertight. Structurally sound. Robbins welded 6 more drums to cover the remaining holes. Different sizes. Different positions. Each drum creating an internal seal chamber. When he finished, the damaged hull section looked absurd. 7 steel drums welded inside a ship like strange internal tumors. Completely unconventional, but completely watertight. His supervisor, Albert Morrison, inspected the work at 1,600 hours. His first response, "What the hell did you do?" Chapter 1. The engineering problem. Morrison stared at the steel drums welded inside the ship's hull. 23 years of shipyard experience. Never seen anything like this. The repair was completely outside standard procedures. Completely unconventional. Completely wrong according to every manual and regulation. Except it worked. Morrison tested the welds. Ran his inspection gauge around each drum. Checked for gaps. Checked for penetration quality. Checked for structural integrity. The welds were solid. Professional quality despite Robbins being a new welder. The drums were securely attached. The damaged areas were sealed. Water couldn't penetrate. He ran a leak test. Standard procedure. Fill the section with water. Check for seepage. The damaged section held water for 45 minutes with 0 leakage detected. By comparison, standard external patches typically showed minor seepage that required additional sealing. The drum method was actually better. Morrison called his supervisor, William Hartley, the yard's chief engineer. Hartley arrived at 1,700 hours, examined the drums, ran his own tests. His assessment was similar to Morrison's. Unconventional, unprofessional appearance, but functionally superior to standard repairs. The problem, Hartley said, is that we're thinking about this wrong. We're seeing it as a repair. It's not a repair. It's something else. Robbins, standing nearby but not speaking, listened. Hartley continued. Standard hull repairs restore the hull to original condition. Replace damaged steel with new steel. Make it like the damage never happened. But this approach doesn't restore anything. It creates internal compartments. The damaged area becomes a sealed chamber. The ship's interior volume increases. The buoyancy characteristics change. Morrison understood immediately. The drums add volume without adding weight. Empty drums are essentially air chambers. Sealed air chambers inside the hull. That increases the ship's total buoyancy. Exactly. This damaged section, with these drums installed, might actually be more buoyant than the undamaged hull, because the drums displace water volume but add minimal weight. The net effect is increased flotation. This was interesting from an engineering perspective, but from a practical shipyard perspective, it was problematic. The repair didn't follow established procedures, couldn't be easily documented, couldn't be inspected using standard methods, couldn't be approved by the usual certification process. But it worked better than standard repairs. That was undeniable. The question was whether works better, justified, violates procedures. Hartley made a decision. I want to test this properly. Not just leak testing. Full structural testing. Load testing. Flotation testing. If this method actually improves buoyancy, that's significant. If it's just a weird repair that happens to work, then it's a curiosity. But if it's systematically better than standard repairs, that's worth investigating. He turned to Robbins. You're reassigned. Temporarily. You're going to work with our engineering team. We're going to test this drum welding technique properly. Find out if it's actually useful or just lucky improvisation. Over the next 3 weeks, Robbins and the engineering team tested the drum method on 6 different damaged ship sections. Different hull shapes. Different damage patterns. Different drum configurations. Each test measured structural strength, water resistance, buoyancy changes, weight additions, cost compared to standard repairs, time required for implementation. The results were consistent. The drum method provided equal or superior structural strength, better water resistance, significantly increased buoyancy, approximately 15% higher than undamaged hull sections. Minimal weight addition. Each drum weighed 22 kilograms empty versus 45 kilograms for equivalent steel patches. Lower cost. Drums were cheaper than cut steel plates. Faster implementation. Welding drums took less time than fabricating and fitting custom patches. The engineering data was compelling. The drum method wasn't just an acceptable alternative to standard repairs. It was demonstrably superior by multiple metrics. That raised a new question. If this method was better, why wasn't it standard practice? Chapter 2. The Flotation Principle. The answer to why drum flotation wasn't standard practice was simple. Nobody had thought of it. Ship repair focused on restoring damaged vessels to original specifications. The goal was always returning the ship to its pre-damaged state. Repairs were about replacement, not innovation. But Robbins hadn't been trying to innovate. He'd been trying to solve an access problem. The difficult welding angle. The awkward position. He'd improvised a solution that happened to be better than the standard approach. Accidental innovation driven by practical constraints. Hartley recognized the broader implication. If adding sealed chambers increased buoyancy, that principle could be applied beyond ship repair. It could be applied to ship design, even to structures that weren't ships. On November 24, 1942, Hartley presented his findings to the Admiralty. Not the full Admiralty Board, just Captain Edward Hughes, the liaison officer for naval construction projects. Hartley explained the drum welding discovery, showed the test data, demonstrated that adding sealed chambers increased flotation capacity substantially. Hughes listened, reviewed the data, then asked the question that mattered. What's the application? Ship repair is useful, but we're repairing ships faster than Germany is sinking them. The bottleneck isn't repairs. It's something else. Hartley didn't have an immediate answer. The drum welding was interesting. The flotation principle was sound. But Hughes was right. The practical application wasn't obvious. Ship repair wasn't Britain's critical problem in 1942. Hughes provided context. The real problem is ports. We're planning operations in Europe. Eventually, we'll invade France. When we do, we'll need ports to supply the invasion force. But German forces will destroy the French ports before we capture them. They did it at Brest, at Cherbourg, at every port they've abandoned. Demolitions, scuttled ships, destroyed docks. When we take those ports, they'll be unusable for months. So we need portable ports, Hughes continued. Something we can bring with us. Deploy quickly. Use immediately. We've been working on designs. Floating piers, pontoon bridges, various concepts. But the fundamental problem is flotation. We need structures that float reliably, that remain stable in rough seas, that can support heavy equipment without sinking. Your drum principle might be relevant. Hartley saw the connection. You're building floating structures. We've demonstrated that sealed chambers increase flotation. If we apply that principle to your floating piers, we could increase their load capacity, make them more stable, more buoyant. Exactly. The question is scalability. Can you create sealed flotation chambers large enough for harbor-scale structures? Your test was ship-sized drums. We're talking about structures measuring hundreds of meters. The engineering challenges are different. Hartley returned to Southampton, assembled his engineering team, included Robbins because the concept originated from his work. The assignment: design large-scale flotation chambers based on the drum welding principle. Structures capable of supporting harbor equipment, piers, roadways, mooring points, everything needed for a portable port. The design process took 3 months. The team tested multiple configurations, different chamber sizes, different materials, different structural arrangements. The principle remained consistent. Create sealed chambers that displace water without adding significant weight. Maximize volume-to-weight ratio. Achieve maximum flotation with minimum materials. By February 1943, they had a working design. Concrete caissons, 60 meters long, 18 meters wide, 12 meters high. Hollow interior with multiple sealed compartments. Each caisson weighed 6,000 tons when empty, but could displace 12,000 tons of water. Negative buoyancy when flooded. Positive buoyancy when sealed. Could be towed across water like ships. Could be sunk into position by flooding specific compartments. Could support roadways and equipment once positioned. The design was elegant, simple, based entirely on Robbins' accidental discovery. Sealed chambers create flotation. Scale the chambers up and you can float anything, even harbors. Chapter 3. Project Mulberry. The Admiralty approved the design on March 8, 1943. Project Mulberry, code name for the portable harbor system. 2 complete harbors would be constructed. Mulberry A for American forces, Mulberry B for British forces. Each harbor required 146 massive caissons, plus additional floating piers, roadways, and breakwaters. The construction scale was unprecedented. The caissons alone required 330,000 tons of concrete, 31,000 tons of steel reinforcement. The project would employ 45,000 workers across Britain. Construction would take 14 months. Everything had to be completed before June 1944, before the invasion date. Robbins was assigned to the construction team at Portsmouth. His job: supervise caisson welding, ensure the sealed chambers remained airtight, train other welders in the flotation chamber technique. The 22-year-old who'd accidentally discovered the principle was now responsible for implementing it at industrial scale. The first caisson was completed on April 20th, 1943. Tests began immediately. The caisson was towed into Portsmouth Harbor. Flotation tests confirmed the calculations. The structure floated with 2.3 meters of freeboard, stable in calm water. Load tests followed. Equipment was positioned on top. The caisson remained stable under loads up to 800 tons. Ballast tests demonstrated controlled sinking. Flooding specific compartments dropped the caisson to the harbor floor in controlled manner. All tests successful. Production accelerated. By July, 12 caissons were complete. By October, 47. By January 1944, 103. The construction sites operated 24 hours daily. 3 shifts. Continuous concrete pouring. continuous steel welding, continuous quality inspection. The pace was relentless. But problems emerged. The sealed chambers required perfect welds. Any leak compromised flotation. Any water ingress reduced buoyancy. Robbins' team inspected every weld, tested every seal, found failure rates around 8%. 8% of welds showed minor leaks. Not catastrophic, but problematic when scaled across 146 casings with hundreds of chambers each. The solution required additional quality control. Robbins developed a testing protocol. Each chamber was pressurized with air. Pressure held for 30 minutes. Pressure drop indicated leaks. Failed chambers were identified, re-welded, retested. The protocol added time to construction but reduced failure rate to 1.2%. The work was exhausting. 14-hour days. 7 days per week. Robbins lost 18 pounds between April and December 1943. Most workers showed similar stress. But the deadline was absolute. June 1944. The invasion date was set. The harbors had to be ready. By March 1944, all 146 casings were complete. Additional components were finished. 23 floating piers, 10 pierheads, 93 floating roadways. The complete Mulberry system ready for deployment. The components were positioned along the southern English coast, waiting for invasion orders. On June 6, 1944, the invasion began. D-Day. Allied forces landed on 5 Normandy beaches. Initial objectives secured by evening. But the beaches themselves weren't suitable for sustained supply operations. Deep water ports were needed. Ports that didn't exist on the Normandy coast. Ports that would have to be created. June 7th, the Mulberry components began crossing the English Channel, towed by tugboats. 160 tugs pulling 146 casings, plus hundreds of additional components. The crossing took 3 days. Rough seas, German coastal artillery fire, mines, chaos. But the structures survived. The sealed chambers maintained flotation. The casings arrived at the designated Normandy positions. Installation began June 9th. The casings were positioned, flooded, sunk into place, connected to form breakwaters, floating piers attached, roadways installed. By June 12th, Mulberry A was partially operational at Omaha Beach. Mulberry B was operational at Gold Beach, both harbors capable of handling ships and cargo. The structures that Robbins had accidentally conceived were now functioning as intended. Floating harbors, created from sealed chambers, based on the principle discovered by welding drums inside a damaged ship hull 18 months earlier. Chapter 4. The Storm. The storm hit on June 19, 1944. Weather forecasters called it the worst channel storm in 40 years. Winds exceeding 55 kilometers per hour. Waves reaching 3 meters height. Sustained for 3 days. The kind of storm that would test any harbor's structural integrity. For floating harbors assembled 13 days earlier, the test was brutal. Mulberry A at Omaha Beach took the worst damage. The American-built casings used slightly different construction methods than British designs. Less reinforcement in the sealed chambers. Less robust welding protocols. The storm exposed these weaknesses. By June 20th, 8 casings had structural failures. Chambers flooded. Buoyancy lost. The casings sank incorrectly or broke apart. Floating piers detached. The entire harbor became unusable. Mulberry B at Gold Beach survived. The British construction methods, specifically Robbins' welding protocols and chamber testing procedures, held. 3 casings showed minor damage. No catastrophic failures. The sealed chambers maintained integrity. The harbor remained operational throughout the storm. By June 22nd, when the storm passed, Mulberry B was handling 7,000 tons of supplies daily. The comparison was stark. Identical design, different construction quality. One harbor destroyed, one harbor functional. The difference was attention to detail. Specifically, attention to the sealed chamber welding that maintained flotation under stress. American engineers visited Gold Beach on June 24th, examined the surviving British casings, documented the construction differences. Robbins was assigned to brief them, explain the welding protocols, demonstrate the chamber testing procedures, show why the British structures survived when American structures failed. The briefing occurred on June 26th. Robbins explained the pressure testing protocol, the 30-minute hold time, the 1.2% acceptance threshold for leaks, the rewelding procedures for failed chambers. The American engineers took notes, asked technical questions. One engineer, Lieutenant James Peterson, asked the critical question, "Why didn't we know about these protocols? We built to the same design specifications." Robbins didn't have a diplomatic answer. The design specifications showed what to build, not how to build it. The welding quality requirements were there, but the testing protocols weren't. We developed those during construction, trial and error, finding what worked, implementing it systematically. Peterson understood. So you invented quality control procedures that weren't in the original design, and those procedures made the difference between success and failure. Yes, sir. The design was sound, but executing the design required specific techniques, especially for the sealed chambers. Any leak reduces flotation. Under storm conditions, even minor leaks become critical. The chambers that held were chambers that passed rigorous testing. The American engineers recommended immediate reconstruction of Mulberry using British construction protocols, but the recommendation was rejected. Too time-consuming, too expensive. Instead, American forces would rely on Mulberry B. The single surviving harbor would service both American and British supply needs. Higher capacity utilization, more ships, more cargo, more operational strain on the surviving structure. Robbins' team was assigned to maintain Mulberry B, inspect the caissons daily, monitor for storm damage, repair any emerging problems. The harbor became Britain's most critical infrastructure in France. Without it, supply lines would collapse. The invasion would stall. The entire European campaign depended on structures that one 22-year-old welder had accidentally conceived. Between June 22nd and December 31st, 1944, Mulberry B handled 2.5 million troops, 500,000 vehicles, and 4 million tons of supplies. The harbor operated at 150% of design capacity, exceeded all performance expectations, remained functional despite stress levels that should have caused structural failure. The engineers analyzed why. The conclusion was consistent with Robbins' original discovery. Sealed chambers provide extraordinary flotation capacity. The redundancy built into multiple chambers meant that even with some failures, sufficient buoyancy remained. The principle worked at scale exactly as it had worked on that damaged Liberty ship in November 1942. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly. Chapter 5. Scaling the Principle. The success of Mulberry B attracted attention from civil engineers. The principle, sealed chambers creating flotation, had applications beyond military harbors. Post-war reconstruction would require similar technology. Bridges, docks, marine structures, all would benefit from the engineering lessons learned at Normandy. In August 1944, Robbins was temporarily reassigned to London. The Ministry of War Transport wanted documentation, complete technical specifications for the flotation chamber system. Not just the caisson design, the entire methodology. How to calculate chamber volume, how to determine optimal chamber configuration, how to test chamber integrity, how to maintain structures under operational stress. Robbins worked with a team of civil engineers. The project took 3 months. The resulting document was 247 pages, titled Floating Structure Design Manual, Principles of Sealed Chamber Flotation. It covered everything from basic physics to specific welding techniques, mathematical formulas for calculating displacement, tables for determining required buoyancy based on structure weight, detailed protocols for chamber testing and quality control. The manual became classified, not because it contained military secrets, because the Mulberry project itself was classified. The Germans knew about the harbors, hard-to-hide 146 massive concrete caissons. But the engineering details remained secret. How the structures were built, why they worked, what made them successful. That information had post-war commercial value. Britain wanted to maintain competitive advantage in marine engineering, but the principles leaked. Engineers talk to engineers. Technical knowledge spreads regardless of classification. By 1945, shipyards across Britain were experimenting with sealed chamber flotation. By 1946, commercial applications were appearing. Floating dry docks, temporary bridges, marine platforms, all using variations of Robbins' original principle. The Dutch were particularly interested. Post-war Netherlands faced massive reconstruction challenges. Destroyed bridges, damaged harbors, flooded polders requiring drainage. The sealed chamber principle offered solutions. Floating structures that could be positioned quickly. Infrastructure that didn't require traditional foundation construction. Temporary solutions that could remain operational for years. In March 1947, Robbins received an invitation. The Netherlands Institute of Engineers wanted him to present at a conference in Amsterdam. Topic: Practical applications of sealed chamber flotation in marine infrastructure. The invitation was surprising. Robbins wasn't an engineer. He was a welder. Self-taught beyond his basic certification. No university education. No formal engineering training. Just practical experience building structures based on a principle he'd discovered by accident. He accepted. The presentation occurred on April 15, 1947. Audience included 340 engineers from 12 countries. Robbins spoke for 90 minutes. Explained the original discovery. The drum welding in Southampton. The transition to caisson design. The construction challenges. The storm survival. The operational success. He focused on practical details rather than theory. What actually worked? What failed? What they learned through trial and error. The response was enthusiastic. Engineers wanted technical details, specific measurements, material specifications, testing protocols. Robbins couldn't answer all questions. His knowledge was experiential, not theoretical. He knew what worked, but couldn't always explain why in engineering terms. Professor Jan de Groot from Delft Technical University approached him after the presentation. Mr. Robbins, your work demonstrates something important. Engineering innovation doesn't always come from theory. Sometimes it comes from practical necessity, from solving immediate problems with available materials, from accidents that reveal principles. De Groot continued. The sealed chamber concept isn't new physics. Naval architects have understood displacement and buoyancy for centuries. What's new is the application, using sealed chambers structurally, building them into large-scale marine infrastructure. That innovation came from your practical work, not from academic research. That's valuable. He made a proposal. Delft University is establishing a research program in marine structures. We need people with practical knowledge, people who've actually built these systems. Would you consider teaching? Not traditional lectures. Practical courses. Show students how things are actually constructed, how real engineering problems are solved. Chapter 6. Post-war applications. Robbins taught at Delft University from 1948 to 1952. Part-time instructor. His courses focused on practical marine construction. Students learned welding, structural assembly, quality testing. But more importantly, they learned problem-solving methodology. How to identify engineering challenges. How to develop solutions using available materials. How to test those solutions systematically. The sealed chamber principle evolved during this period. Students and researchers developed new applications. Floating foundations for buildings in soft soil. Submersible platforms for offshore work. Temporary structures for disaster relief. Each application used the same core principle. Sealed chambers provide controllable flotation. Position them correctly, and you can float anything. One particularly innovative application came from a 1950 student project. Floating airport runways. The concept seemed absurd initially. Runways required rigid, stable surfaces. Floating structures moved with waves. How could aircraft land on something that wasn't stationary? The student team, led by Henrik Janssen, proposed a solution. Use sealed chambers to create a floating platform, but add ballast chambers for stability. Control the platform's response to wave motion through active ballasting. When waves created lift on one side, add ballast there. Create a self-leveling system that maintained horizontal stability despite water motion. The concept was tested at 1/10 scale. A 15-meter platform with sealed flotation chambers and controllable ballast. The platform maintained horizontal stability in simulated wave conditions up to 1 meter amplitude. Not perfect stability. Movement variation of approximately 8 centimeters. But potentially sufficient for aircraft operations. The full-scale version was never built. The engineering challenges were substantial. The cost was prohibitive. No immediate military or commercial need existed. But the concept demonstrated the principle's flexibility. Sealed chambers weren't just for static flotation. They could be components in dynamic systems. Active structures that responded to environmental conditions. This broader understanding influenced post-war marine engineering significantly. Oil platforms in the 1960s used variations of sealed chamber design. Offshore drilling rigs floated on seal pontoons, dynamically positioned using ballast control. The connection to Robbins' original work was indirect, but real. The principle he'd discovered welding drums in a ship hulls had evolved into an entire engineering discipline. Robbins left Delft in 1952, returned to Britain, worked as a consultant for marine engineering projects. His expertise was recognized. Projects in Norway, Denmark, France, Italy. Each project involved floating structures. Each applied principles derived from his original discovery. He wasn't designing the structures anymore. Younger engineers with better education handled design, but his practical knowledge remained valuable. How to actually build what designers drew. How to test what theory predicted. How to make engineering concepts work in reality. In 1958, he was awarded the Order of the British Empire, recognition for contributions to wartime engineering efforts. The citation mentioned Project Mulberry, mentioned the floating harbors, didn't specifically mention the drum welding discovery that started everything. Awards rarely capture the complete story. Robbins didn't mind. The recognition wasn't why he'd done the work. He retired in 1975 at age 55. Spent his later years sailing. Built his own yacht using, naturally, sealed chamber flotation principles. The yacht had unusual stability. Rode heavy seas better than comparable vessels. Other sailors noticed. Asked about the design. Robbins explained the sealed compartment configuration. How he'd calculated optimal chamber placement. How he'd tested buoyancy characteristics. Some built similar vessels. The principle spread again, this time through recreational boating. The yacht was named Accidental, a reference to how the whole journey started. One wrong weld. One improvised solution. One accident that became systematic engineering. Robbins sailed Accidental for 18 years. Mediterranean, Caribbean, Atlantic crossings. The yacht performed flawlessly. Proved the principle worked as well for pleasure craft as for military harbors. Chapter 7. Recognition and Legacy. The full story of Mulberry Harbor emerged gradually after declassification. Military historians documented the invasion logistics. Engineering historians analyzed the floating harbor design. But the origin story, how the concept developed from an accident in Southampton Shipyard, remained obscure until 1982. That year, the Imperial War Museum prepared an exhibition on D-Day engineering. The curator, Margaret Fletcher, researched Project Mulberry extensively, interviewed surviving engineers, examined declassified documents, found references to sealed chamber flotation principles developed at Southampton, November 1942. Traced those references back to Hartley's reports. Found Robbins' name. Fletcher contacted Robbins. He was 62, still sailing, reluctant to discuss wartime work. But she was persistent, persuaded him that the story mattered. Not for his personal glory, for understanding how engineering innovation actually happens. How major developments often start from minor accidents. How practical workers solve problems that theoretical engineers miss. Robbins agreed to an interview. For hours recorded on June 8, 1982. He explained the damaged ship repair, the awkward welding angle, the decision to use drums, the surprise when it worked better than standard repairs, the transition from ship repair to harbor design, the construction challenges, the storm, the operational success, everything he remembered from 40 years earlier. The interview revealed details not in official records. How exhausted everyone was during construction, how they worked 98-hour weeks, how 3 workers died in construction accidents, how they weren't certain the caissons would survive actual combat conditions, how the June 19th storm terrified them because structural failure would doom the invasion. Details that made the engineering achievement human, real, difficult, Fletcher asked about the key decision points. When did Robbins realize the drum welding was significant? When did he understand it could scale to harbor-sized structures? When did he believe the project would succeed? Robbins' answer was honest. I never believed it would work at that scale. I was a welder. I understood welding drums to ships. I didn't understand naval engineering. Didn't understand harbor design. Didn't understand logistics. When they told me we were building floating harbors, my thought was, this is mad. This cannot possibly work. But I kept welding, kept testing chambers, kept training other welders. Because orders were orders. Because the deadline was absolute. Because if it worked, thousands of soldiers would survive who'd otherwise die in the invasion. He paused. The answer to your question is, I believed it might work when it survived the storm. June 22nd, 1944, when Mulberry was still floating, still operational, still handling cargo despite 3 days of heavy seas. That's when I thought, we actually did this. We built a harbor that floats. And it works. The Imperial War Museum exhibition, opened in November 1982, included a complete section on Project Mulberry. Robbins' interview was transcribed and displayed. Technical drawings showed the caisson design. Photographs documented construction. Scale models demonstrated how sealed chambers provided flotation. The exhibition explained that major engineering innovations often emerged from unexpected sources. That formal education wasn't the only path to significant technical contribution. That sometimes the right person at the right moment with the right practical knowledge could change outcomes. The exhibition was popular. 47,000 visitors over 6 months. Many were engineers. They studied the technical displays, analyzed the chamber configurations, calculated the flotation mathematics, appreciated the elegant simplicity of the principle. And many asked the same question: why didn't established naval architects think of this first? The answer, provided in exhibition materials, because they were thinking about ship design, not about making ships that were meant to sink in controlled ways, not about using ships as structural foundations. The creative leap required thinking outside traditional categories, seeing ships as something other than transport vessels. That kind of thinking came from someone not constrained by traditional naval architecture training. Chapter 8. The Engineering Philosophy. Robbins gave occasional lectures after the exhibition. Universities invited him. Engineering societies. Professional conferences. His message was consistent. Engineering innovation requires practical knowledge, combined with willingness to violate conventional approaches. At a 1985 lecture at Southampton University, he explained, the sealed chamber principle isn't complex. Every engineer knows water displacement creates buoyancy. Every naval architect understands flotation calculations. The mathematics are straightforward. So why didn't someone invent this earlier? Why did it require an accident in 1942? Because, he continued, engineers were trained to restore things to original specifications. Ship repair meant making damaged ships into undamaged ships. The goal was always returning to the starting condition. Innovation wasn't part of repair work. Repair was about preservation, not improvement. I wasn't trying to innovate. I was trying to finish my assignment despite poor working conditions. The drums weren't a clever solution. They were an expedient solution, something available that would work despite the constraints. If I'd had better access to the damaged area, I would have done standard repairs. The innovation came from necessity, not from planning. This philosophy, necessity drives innovation, became central to Robbins' teaching. He emphasized that engineering education should include constraint-based problem-solving. Give students difficult tasks with limited resources. Make them improvise. Make them work with what's actually available rather than what's theoretically optimal. Modern engineering programs adopted some of these ideas. Practical courses, workshop projects, real-world constraints. But Robbins argued they didn't go far enough. Students should fail, should build things that don't work, should discover through experience what theory misses. Engineering isn't mathematics. It's mathematics plus materials plus fabrication, plus testing, plus failure plus learning from failure. You can't teach that with equations and lectures. His most controversial position, engineering certification, should require practical construction experience. Not just design work, actual building. Naval architects who've never welded a ship don't understand how their designs will actually be built. Civil engineers who've never poured concrete don't understand construction limitations. Mechanical engineers who've never machined parts don't understand manufacturing constraints. Theory without practice produces elegant designs that fail during implementation. Not everyone agreed. Academic engineers defended theoretical training, argued that understanding principles mattered more than manual skills, that designers shouldn't need to be builders, that specialization produced better outcomes than generalization. Robbins countered with Mulberry Harbor. The initial caisson designs were elegant, beautiful engineering. They would have worked perfectly if they'd been built perfectly. But construction isn't perfect. Welds have defects. Concrete has air pockets. Assembly introduces stresses not accounted for in design. The structures that survived were structures built by people who understood these practical limitations, who tested rigorously, who compensated for real-world imperfections. That knowledge didn't come from design theory. It came from construction experience, from welding thousands of chambers, from seeing which ones leaked and which ones held, from learning through trial and error what actually worked versus what should theoretically work. The debate continued throughout the 1980s and 1990s. Engineering education evolved slowly. Some programs added practical requirements. Others remained primarily theoretical. The balance between design knowledge and construction knowledge remained contested. But Robbins' central point was hard to dispute. Major engineering innovations often came from people facing practical constraints, from builders encountering real problems, from workers improvising solutions with available materials, from accidents that revealed possibilities theorists hadn't considered. The sealed chamber principle was one example. There were others. The microwave oven invented by engineer noticing radar equipment melting chocolate. Vulcanized rubber discovered accidentally when rubber compounds contacted hot stove. Penicillin found when mold contaminated bacterial cultures. Safety glass created when cellulose nitrate coating accidentally protected glass from shattering. Innovation history was full of such accidents, each revealing that theoretical knowledge alone wasn't sufficient. That practical work, combined with observation, combined with willingness to recognize unexpected results, produced breakthroughs theory couldn't predict. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly. Chapter 9. Modern Applications. The sealed chamber principle Robbins discovered has become ubiquitous in modern marine engineering. Though most engineers using it today don't know its origin story, don't know about the Southampton Shipyard, don't know about the drums welded into Liberty ship hulls, don't know it started as an accident. Modern oil platforms use sealed pontoons for flotation. The pontoons are sophisticated versions of Robbins drums. Steel structures with watertight compartments, providing controlled buoyancy for structures weighing thousands of tons. The design principles are identical to 1942 caissons. Scale is larger. Materials are better. But the underlying concept is unchanged. Floating bridges use the same principle. Modern military pontoon bridges, civilian floating road sections, marine terminals, all rely on sealed chambers providing buoyancy. The calculations are more precise than Robbins' work. Computer models optimize chamber placement, but the basic physics hasn't changed. Displacement creates lift. Sealed chambers control displacement. Simple mechanics that work reliably. Submarine design evolved using related principles. Ballast tanks are essentially controlled flotation chambers. Flood them to submerge. Empty them to surface. The concept of using sealed chambers for controlled buoyancy changes applies to submarines as much as to harbors. Different application. Same principle. The most direct descendant of Mulberry Harbor is the modern floating dry dock. These structures use sealed chambers to float while empty. Sink when ballast tanks flood. Allow ships to enter, then surface by pumping out ballast. The ship lifts with the dock, enabling repairs above waterline without traditional dry dock facilities. Robbins visited a floating dry dock in 1988. Singapore Shipyard. Massive structure capable of lifting 100,000-ton vessels. He watched it operate. saw it sink, saw it rise, recognized his principle at industrial scale far beyond what he'd imagined in 1942. His comment to the yard manager: "This is just steel drums. Very large steel drums. But the same idea. Sealed chambers. Controlled flotation. It's extraordinary how far a simple principle can scale." Climate change has created new applications. Rising sea levels threaten coastal infrastructure. Floating structures offer adaptation strategy. Floating homes, floating cities, floating farms, all using sealed chamber flotation. The Netherlands has been particularly active. They face existential threat from sea level rise. Floating structures aren't theoretical there. They're survival strategy. In 2019, Dutch architects completed Skunship, floating neighborhood in Amsterdam. 46 homes on floating platforms. The platforms use sealed flotation chambers. Rise and fall with water level. Remain stable despite tidal variations. Total platform area, 8,000 square meters. Population, 102 residents. The neighborhood demonstrates that sealed chamber flotation works for permanent civilian housing. Not just military infrastructure. Not just temporary solutions. Long-term habitation. The design explicitly references Mulberry Harbor. The architects studied the caisson engineering, adopted similar chamber configurations, updated materials and methods, but kept core principles. They acknowledged that their work built on foundation laid by wartime engineers. That innovation from 1942 remained relevant in 2019. That good engineering principles transcend their original context. Robbins died in 2016 at age 96. He never saw Skunship completed, but he followed the project, reviewed the plans, provided informal advice to designers. His last professional contribution was suggesting chamber testing protocols for the Amsterdam platforms. The same protocols he developed in 1943. Still applicable, still necessary, still ensuring that sealed chambers held pressure and maintained flotation. His final recorded comment on sealed chamber flotation from 2015 interview: "I spent 70 years watching this principle evolve. Saw it scale from ships to harbors to bridges to platforms to neighborhoods. The applications changed. The engineering sophistication increased. But the fundamental physics remained identical. Water displacement creates lift. Sealed chambers control displacement. Everything else is just implementation details." That's what I learned welding drums in 1942. That's what still applies today. Chapter 10. The accident that changed warfare. D-Day succeeded for many reasons. Air superiority, naval bombardment, deception operations, tactical planning, individual courage. But logistics determined whether tactical success translated into strategic victory. Without supply capacity, beachheads remain beachheads. Without ports, armies starve. Without harbors, invasions fail. Mulberry handled 2.5 million troops and 4 million tons of supplies between June 1944 and December 1944. Without it, the Normandy invasion couldn't have sustained its momentum, couldn't have broken out from the beaches, couldn't have liberated France. The harbor wasn't auxiliary infrastructure. It was critical infrastructure, essential for success. And it existed because a 22-year-old welder couldn't access a damaged hull section properly. Because he improvised with available materials. Because he welded drums instead of plates. Because that accident revealed a principle. Because that principle scaled the harbor design. Because sealed chambers provided flotation for caissons that survived storms and supported invasion logistics. Military historians debate counterfactuals. What if Mulberry had failed like WWII? What if the June 19th storm had destroyed both harbors? What if sealed chamber flotation hadn't been discovered? The consensus: D-Day either fails completely or succeeds months later with much higher casualties. The timing and logistics of the invasion depended on portable harbor capability. That capability depended on floating caissons. Those caissons depended on sealed chamber flotation. The causal chain traces back to Southampton Shipyard, November 1942. Thomas Robbins didn't see it that way. In his 1982 interview, he said, "I welded some drums. That's all. Other people designed the harbors. Other people built them. Other people operated them. Thousands of people made Mulberry work. My contribution was tiny, accidental. I happened to be the right person in the right place doing the wrong thing in a way that turned out to be right. But that understates causation. Without the initial discovery that sealed chambers provide superior flotation, the harbor design wouldn't have worked. The principle was foundational. Everything else built on it. The architects needed the principle before they could design the structures. The builders needed the principle before they could construct effectively. The operators needed the principle to maintain the harbors under stress. The principle came first. Everything else followed. That's what makes accidents significant in engineering history. Not that they happen. Accidents always happen. What matters is recognition. Seeing that something unexpected is actually useful. Understanding why it works. Developing systematic applications. Scaling from accident to principle to methodology to infrastructure. Robbins had that recognition. When the drums made the hull more buoyant, he didn't just note it and move on. He thought about it, tested it, documented it, shared it with supervisors who recognized its significance. The accident became innovation because Robbins and others turned it into something reproducible and scalable. Modern engineering culture tries to eliminate accidents. Systematic design, rigorous testing, quality control, standardization, all aimed at making outcomes predictable, all valuable for reliability, but also potentially limiting for innovation. Because accidents reveal possibilities that systematic design doesn't explore. Combinations not considered. Configurations not tested. Applications not imagined. The sealed chamber principle was obvious in retrospect. Naval architects knew about displacement and buoyancy, but they weren't thinking about making things designed to sink in controlled ways. Weren't thinking about ship sections as structural foundations. Weren't thinking outside traditional ship design categories. The accidental discovery opened that conceptual space, made the familiar principle available for unfamiliar applications. That's the broader lesson from Robbins' story. Not that accidents are good. Not that training is unnecessary. Not that systematic engineering is wrong. But that innovation often requires seeing familiar things in unfamiliar contexts. Applying known principles to new situations. Being willing to notice when accidents produce useful results instead of just producing failures. November 3rd, 1942. Southampton Shipyard. A young welder kicks a bottle. Decides to use drums instead of plates. Creates better flotation accidentally. 18 months later, that accident enables the liberation of Europe. The causal connection seems improbable, but historical documentation confirms it. Small moments. Practical decisions. Unintended consequences. That's how innovation actually happens. Not according to plan. According to accident and recognition and systematic development of accidental discoveries. Thomas Robbins, welder, who discovered a principle. Thomas Robbins, engineer, who developed that principle into systems. Thomas Robbins, teacher, who explained how practical knowledge produces innovation. Thomas Robbins, sailor, who proved the principle worked for recreation as well as warfare. Thomas Robbins, 1920 to 2016, who changed marine engineering by making one wrong weld that turned out to be exactly right. Stories like this deserve to reach those who value them. If this account held meaning for you, consider helping others discover it. A like tells the algorithm to share this with similar audiences. Subscribing to the channel and enabling notifications ensures these stories reach you when new accounts are published. Your engagement becomes a form of historical preservation, connecting those who seek this knowledge with those who've taken time to document it properly.